So we've got a decent length question here. It's about sort of waves and how evidence from waves relates to the idea of the Big Bang theory and the expanding universe. So we start with the teacher. They're demonstrating circular waves in a ripple tank. So here we can see our circular waves. So our source must be in the middle here, and our waves will be spreading out from that source. And it asks us initially to show on diagram 1 the wavelength of the waves. Well, this is a crest of a wave. This is the crest of a wave. So wavelength from the peak, from the crest of one wave to the next, is that distance there. So that's our wavelength. The teacher moves the source of the waves across the ripple tank. So now we can see this, by moving the source, we get this strange effect where here we can see the waves are getting squashed together, or seem to get squashed together, whereas on this side, the waves seem to spread out. And that's what happens when you move a source in one direction. If you're in front of the source, the waves come with the wavelength closer together. And if the source is moving away from you, the waves or the wavelengths stretch out. So it asks us in diagram 2, the observed wavelength of the waves that X has. Well, we can see the wavelength has got bigger, so that is increased. Okay, in diagram 2, the frequency of the waves. So what's the frequency? The frequency is how often the waves are arriving, how many waves in a second past this point. Okay, so if the waves are, or the wavelengths are further apart, larger wavelength, the wave will still be traveling at the same speed, here and here and here, but the peaks are further apart, so they will be less frequent. The number of peaks passing that point every second will be less, so the frequency will have gone down. It's decreased. And then it asks us to actually take measurements from the diagram to determine the wavelength. So you get your ruler out, and the obvious thing to measure, again, would be from there to there. But actually, that's not very accurate. You're only taking one measurement there, and we've got a few wavelengths we can measure. So what you really should do if you're getting a few readings like this is you measure across those few wavelengths, so from there to there. And then you've got 1, 2, 3 wavelengths, and so you take that measurement and then you divide it by 3, and that will give you a more accurate reading of the wavelength. And in this instance, if you got your ruler and took those measurements, you would find it comes to about 17. 17 what? Well, it says, give us the units, 17 millimeters. Okay, so the teacher uses a ripple tank, and they're modeling light observed from different distant galaxies. Okay, and we can see when we look at distant galaxies that their light does have the wavelength increased. Okay, what's the name of this effect? This is called redshift. Because if you've got some light with a certain wavelength, if you stretch that wavelength, you are moving the color of that light towards the red end of the spectrum. Red light has a longer wavelength than, say, blue light. What does this increase in wavelength tell us about the movement of most galaxies? It means that they are moving away from us. Now, explain how this observation supports the Big Bang theory and the formation of the universe. So it would be nice just to say, well, the galaxies are all moving away from us, therefore there must have been a Big Bang. But that's an oversimplification. That won't get you all the marks here. What you need to say actually is, when we look at the galaxies that are close to us, they are moving away. When we look at the galaxies that are further away than that, the more distant galaxies, they are also moving away, but they are also moving away faster. And that suggests, one, that the galaxy is getting bigger, is expanding, but it also suggests that they originated from a point. Not necessarily where we are, but they originated, they're expanding from a central point. And that suggests the Big Bang. Okay, so the fact the universe is expanding is suggested by, like I said, the key point: the further away a galaxy is, the the faster it's moving away from us. And so, if we looked at these galaxies, we would find that these have got small amounts of redshift, but these galaxies that are further away, they have a larger redshift and therefore are moving away faster. So, state one other piece of evidence that supports the Big Bang theory, because this evidence sort of suggests it, but there are other theories that can also use to explain these observations. So there is one other main piece of evidence you're expected to know about, and that is cosmic microwave background radiation. Bit of a mouthful. What is it? Is when we look up into the night sky, we find that throughout the universe there is this low level of microwave radiation, pretty much wherever we look. So that is seen as evidence because it's kind of the echo of the Big Bang. The Big Bang produced a lot of radiation, and it's been stretched and slowed down and spread out until it's in the microwave section of the electromagnetic spectrum. Okay, if you can't remember all that, if you can remember CMBR, generally they will accept that as an answer, but it's cosmic microwave background radiation. Okay.